All right. So we're absolutely delighted to have Nishi back here. Every time he's been up here, he's given a spectacular talk. So I hope this time will not be different.
Thank you for hyping the crowd up. It's of course fantastic to be back. Thank you so much for the invitation, and it's a pleasure to talk here. So I'm going to talk about using like quantum field theory methods to say something about the cohomology of moduli spaces, and specifically about the modular space of curves as one example. And this is based on a paper from earlier this year. And so Dawn Zagier kindly contributed an appendix to this paper. And I also want to mention like joint related work with Karen Vogtmann on this. So the main player or the main character of this talk is this commutative graph complex. And it's a bit of a weird object that really kind of plays a focal role in the middle of physics and mathematical physics and topology and algebraic geometry. And it's kind of creeping outwards into more and more areas of mathematics. So that's very cool, I think. And it's also a very combinatorial object. So this is in the center. And I'm going to explain to you like what this object precisely is and what it does. So the idea is, so I'm going to give like some rough idea to not lose everyone if I start with a definition, but I will give the concrete definition later. So the idea is to just make a chain complex. And we want the chains to be graphs. And we want the boundary of a graph we want the boundaries to be like natural operations of the graph. And in this case, we are thinking about all edge contractions or deletions. Deletions, but let's just stick to all edge contractions. And such a complex was written down by Kontsevich in '93. So this goes back to Kontsevich. But it's very much inspired from Feynman diagrams and a story around Chern-Simons theory, and also ribbon graphs and the modular space of curves and the modular space of graphs. But it's also very much inspired from Feynman diagrams. So to just only for the physicists, maybe some brief suggestive equation. So in physics, people really like these graphs that are equipped with legs. So they have some edges and vertices like a normal graph, but they also have legs that are sort of dangling edges that are attached somewhere fixed in space. So we can think of this graph as a graph without any automorphisms. Because these legs here, you can imagine them to be like pinned with a little pin to some board, and you cannot move around the edges. So what we want is we want to act with a boundary operator on this graph. And the idea is to get something where we contract like all the edges of the graph we have 4 possibilities. We can contract all the 4 edges, and we get something like this. So 4 times this kind of ice cone graph here. And I'm mentioning this because this is also a very natural operation in physics, where one likes to think about these edge contractions of graphs as kind of giving or determining the shape of IR singularities. But one cannot just do this and define this like this, because what we want from a chain complex is that the differential squares to 0. We need to get some signs into the game as well. And this is where the actual definition of the graph complex comes into play, because, yeah, there's a trick how we can associate an orientation to each graph, and this gives us the necessary signs. So here's the definition. Definition of the graph complex, GCG. So to define it, we take all pairs of a graph, capital G, and some object sigma. So, and we only take these pairs up to isomorphism. And what we want is, so the graph is supposed to be connected. It has to have rank G, so meaning that the fundamental group of the graph is supposed to have rank G, or it has G loops. So, for instance, we can have this kind of graph here. Yeah, oh, I forgot one condition. So we want to have the vertices, they have degree larger or equal to 3. So we have a minimal vertex degree. So for instance, this graph here is allowed. More complicated one is this graph. And here you can see that multiple edges are also allowed to, so multiple edges between a pair of vertices is allowed. And we can also have a graph like this one here, which is this handlebar-shaped graph, where we have 2 self-loops. So self-loops are also allowed. And now the sigma is an ordering of G's edges. So it's just a map that takes the edges of the graph and assigns some number to them, which we can take to be in between like 1 and the total number of edges. So we just label the edges with integers. So now this graph complex is the vector space generated over the rationals, which is generated by such pairs. But we mod out by a relation, by a very simple relation, actually. So the relation is just that, or it's a family of relations. So we have one relation for each graph and one relation for each permutation of these labels. So for each G and some permutation of the edge labels, we want to identify the generator where we permute around the edge labels by some arbitrary pi. So we just change the labeling of the edges, and we want this to be equal to the graph where we just leave the edge labeling alone, but we want to pick up a sign, and the sign is precisely the sign of the permutation with which we permuted the edges around. So here's a non-example. So we can take this graph here, this triple edge graph. We can just apply the relation and flip 1 and 2. So when we pick up a minus sign. And of course, this graph is now isomorphic to the first graph. So just did nothing to the generator, we just picked up a sign. So this means that this is equal to minus the thing that we started with, which is labeled in the trivial way. And this means that the generator is 0. So this is not a good graph. And you can see that this kind of relation comes from an automorphism of the graph. So because we have an automorphism that reverses this change of this ordering, we have this generator being 0. So for a proper example, an example is this tetrahedron graph, which we can just give some labels. And you can check that this graph, even though it has many automorphisms, none of these automorphisms changes the labeling of the edges by an odd permutation. So this has no orientation changing automorphism. And this means that this is orientable, or this no odd automorphism. And so this gives a generator of this graph complex. Actually, of the graph complex with 3 loops, because this graph has 3 loops.
So is your sigma bijective?
Yes, this has to be bijective, yeah.
1/5 is the 4.
Oh, yes. Sorry about that, and thanks for paying attention. Okay, this is not a chain complex yet. We need a grading. The grading is simple, so the K chains are just defined by restricting to the graphs with K edges. So this is very simple. So for instance, this generator there, it has 6 edges, so it lives in degree 6. And now we can just compute the support. So these chain groups or chain spaces, actually, because it's all over a field, they have support for the degree in between G and 3G minus 3. Because the lower bounds, like the graphs with a specific loop number with the least number of edges, And these are these graphs where you just have a tadpole. So this is G many petals to this rose. And here we have 3 regular graphs. So these have the most edges for a fixed loop number. And now we need the differential on this complex. So with all this definition, the differential is now very simple. So this just makes Ck of GCG to Ck minus 1 of GCG. And it just takes a generator, G sigma, to the alternating sum, or to the sum of the edges, first of all. And for each edge, for each graph, we then contract the respective edge we sum over. And we just alternate over these contractions with respect to this ordering. Yes, please. Yes, this is also a non-example. It's true. So this is I didn't want to keep things simple, but this tells you immediately that you can remove. This is a strict inequality, actually. Okay. Yeah, we alternate here with the ordering. This is sigma ordering over these edges. And the induced ordering of the edges also comes by the canonical way to remove this edge from the specific ordering. So we have a canonical way to get a new ordering of the edges of this reduced graph. And then one can easily check that this squares to 0. So this is a proper differential. So maybe if I yeah, I can give a brief example. So this is an example of this story. So we can take this, hope you can see it, this football-shaped graph like this. And let's say it has some edge labels. So we label these edges here in the middle, 1, 2, 3. And you can see that all the other edges, they are part of some triangle. So if we contract one of the other edges that are not labeled, we will generate a double edge. And by this relation, these graphs will all vanish. So we only need to care about these 3 edges here in the differential. So we can just compute it. And what we get is then this wheel graph. And one way to assign these numbers is then say this is number 1, this is number 2, and these other edge labels, they are canonically inferred to this side. And we have to then we have another edge to contract. So this graph comes from the contraction of edge number 2 here in the middle. But we can also contract these edges 1 and 3. And these give twice the same graph because this graph has an automorphism that flips 1 and 3. And these also don't vanish. So this is this little house-shaped graph. And the numbers end up being these middle edges here again. Any questions? No. Good. So this now defines graph homology. And this is just the simplest, or arguably the simplest instance of a whole family of different like flavors or versions of graph homology. So graph homology is now just defined as usual as the quotient of the kernel of this differential over the image. And we restrict to the degree k, and this is just the number of edges. This restriction to the degree. And this thing is now called, so the specific flavor of graph homology is called even commutative graph homology. All right. That's a good question, and it's something that I prefer not to talk about in detail because it requires knowledge about something called operads. So it comes from operads. This commutative, this graph complex has an operatic interpretation, but then to explain it, you have to know what an operad is, and yeah, it's tricky. Okay. Okay, we'll try this dangerous blackboard. Let's see how I manage. I barely survived. Okay, it's dangerous indeed. Okay, so now we defined it, but why is it actually so interesting? So it's, of course, an entirely combinatorial thing to consider. So it's very simple to describe it, but the surprising thing is that you can use such a simple combinatorial object and it suddenly appears everywhere. So where does it appear in the wild? And of course, I should mention first the original motivation, Kontsevich defined this for. And this is very physical. This is deformation quantization. So this was the original purpose of the graph complex. So this graph complex, it helps you in the process of like going from a Poisson structure to a non-commutative structure or some operad algebra of operators on a Hilbert space, roughly, very roughly. And this way it also relates to many like things that are very interesting in physics, like integrability. Yeah, and solutions to the so-called Young-Baxter equation, which is also a very important physical object. So this graph complex gives generators of a group that acts on the solutions of this Young-Baxter equation. So yeah, but this is but yeah, physicists will know what I'm talking about, but no worries if you're not a physicist. Yeah. Then I should mention, so I already mentioned that this graph complex comes in like all kinds of different flavors, and associated So in this commutative flavor, there are actually two different subflavors. One is the even and the other one is the odd version. And this odd version of this commutative graph complex, it's very much related to Chern-Simons theory. Or in other words, Chern-Simons theory tells you a lot about this graph complex. Or even differently, perturbative Chern-Simons theory tells you a lot about this graph complex. Then there's something called Borinsky Witten theory, which gives a relationship. So this has inspiration from string theory, very much inspired from string theory, this Borinsky-Witten theory, but it gives you a handle on something called hyperkähler manifolds. So there's a relationship between hyperkähler manifolds and odd GC classes, specific odd GC classes, I have to say. And then also for this odd version, there's also applications to knot theory. So the variant of this odd graph complex where you also allow these legs that are important in physics that I had up there. This variant in turn, it tells you all you want to know about so-called Vasiljev invariants in knot theory that are believed to be universal knot invariants. So it also relates to knots a lot. So here's a more recent application of this flavor of the graph homology that I was just talking about. And this is a theorem due to Melody Chan, Søren Galasius, and Sam Payne. Two of these are in the audience. So this is from 21, I think. And their theorem says that this graph homology, it's isomorphic to the top weight cohomology. So there's something called the top weight, the specific subspace of the cohomology of the modular space of curves. So this MG is the modular space of curves, the modular space of Riemann surfaces with rational coefficients. And this is isomorphic to graph homology, as I just described it above. So this is a very recent example. And also just to mention it, there's also further combinations. Yeah, there's also, say, applications to questions or to GLNZ or to the group cohomology of GLNZ. And this is very recent. So this is started by Brown on, and then there's also numerous papers by Brown and Schnetz, Brown, Panzer, Hu, Brown and Chan-Galasius Payne. And it's a very fascinating story that GLNZ, which is like the symmetry group of all lattices, so it's also arguably for physics a very important object. And one nugget of this story that I want to mention, so it's just a specific aspect. I don't have to talk about it much more because I would guess that Melody is also explaining more from the story. But one specific nugget is that you can take a class from the group cohomology of GLNZ, which is a very basic object in mathematics. So you can actually, so this is a specific family of classes. It's all in the stable cohomology of GLNZ. And you can pair these with cycles, or actually not only the cycles, but with chains. So these are just chains in GCG. They have to have the appropriate degree, but there's a pairing that was figured out by Brown. And it was figured out by Brown that this pairing, it evaluates to Feynman integrals. So this is then a linear combination of Feynman integrals. And Feynman integrals are very important in fundamental physics and in the perturbative expansions of quantum field theories.
So this result is a number.
Yes, this pairing. Yeah, it's a polylog is not a number, it's a function. So this is a multiple zeta value. And so, yeah. All right. So these are applications of this graph complex. So now, let me get rid of the dangerous board again. So now I will tell you what is known about this graph homology. Or are there more questions? Sure. You can also do that, yes. And it makes the structure not quite so interesting, but you can also consider this, yes. But it's also helpful for some arguments. And yeah, it plays an important role actually in many arguments. So what's known about this graph complex? So the first thing is a theorem by Wilwacher. In 2015, that first, so to state it, we have to do something strange. We have to form like the direct sum of many different homologies of this graph complex. So we take the direct sum of the degree 2G graph homology of the graph complex of rank G. And it turns out that this object here in its entirety carries a Lie algebra structure. So we can bracket elements of this thing here. And this is also a combinatorial operation on this graph complex. And the theorem by Wilwacher says that this Lie algebra structure gives an object called the Grothendieck-Teichmüller Lie algebra, which is a very mysterious object. So yeah, so this is this Grundig-Teichmoduli algebra. And then the theorem also, Vivacher also proved that in the degrees below this 2G degree, the homology vanishes. So for k smaller than 2G, this homology is 0. And just as a kind of, just to appeal to the physicists a bit more, question is now what's so special about these graphs that have precisely twice the number of edges as loops? And yeah, so this is something that you can understand as these are the graphs, the Feynman graphs, which are logarithmically divergent in 4 dimensions. So these are, so this, the special thing here is a statement, or can be interpreted physically about a statement on log divergent graphs with quadratic propagators in d equals 4. So this is just a side remark for physicists. Sure.
What's the Lie algebra structure?
The Lie algebra structure is plugging. So there's a bracket of like one graph with, say, another graph, like so. And the Lie algebra structure says that you should take this graph and replace a vertex of this graph with this graph from this size in all possible ways, and then do the opposite thing and subtract this from each other. So this gives you a Lie algebra structure. More questions? Yes?
Does the physical perspective give any insight into the vanishing of homology for degree less than 2G?
I don't think so. Probably not. It's yeah. So this vanishing here means that everything that is like superficial, so that is divergent, that's higher divergent, is 0. So everything that's quadratically or like has any higher order of divergence vanishes. And yeah, I mean, it would be fantastic to figure out physical interpretation of this and have like some quantum field theory that tells you these kind of things. But yeah, so yeah, maybe there's some magic quantum field theory that does all this, but so far it's not really known. The closest thing is really this theorem by Brown that relates it all to perturbative expansions of Feynman integrals. So this really gives you like some feeling that there should really be some quantum field theory, some complicated gauge theory or something that does this, but it's not really known.
So when you say logarithmically divergent, you mean only the superficial divergence?
Only superficial divergent, yes. Yeah. Yeah. Yes, but here, not here. No, this is just so. Yeah. Yeah. I mean, can you ask this question again when I'm finished? Because I have to get through the program. But yeah, it's a non-trivial thing how to define it, but this is the rough idea that you want to plug in one graph into another. The details are, yeah, the complication lies in the details. It's not obvious how to do this. Okay. So this is interesting, this Grundig-Teichmoduli algebra. Also because there's another theorem by Brown that says that there's a free Lie algebra that is generated by sigmas, by these sigmas, all in odd degree, that injects into this Grothendieck-Teichmüller Lie algebra. So this is a free Lie algebra. And it lives inside this GRT object. And so, yeah, so some people, some more physicsy oriented people in the audience, they might know this very well from the algebra of multiple zeta values. So yeah, so there's an interpretation of these, or sometimes it's also called F alphabet. Yeah, and these sigmas, so sigma 3 lives in H6 of GC3, and it's represented precisely by this graph that I already mentioned, this tetrahedron graph, and then sigma 5 lives in degree 10 of GC5, and it's this graph with 5 spokes, this wheel with 5 spokes. And an interesting thing here is that this gives rise to an exponentially growing family of classes. So the number of generators in this free Lie algebra grows exponentially. Okay. So finally, you can talk about the new results. So this is more or less what is known about this, this graph homology. I also should mention that also physically very interesting is, so you can say this 2G diagonal is very interesting, the direct sum of all these groups, or these spaces. And below that, it's all 0, but there's an extra conjecture. There's a conjecture, which is very important also in deformation quantization. The conjecture is that H2G plus 1 of GCG vanishes. The conjecture by Kontsevich in this graph complex story. And yeah, it's completely open. So far, no one has found a class in such degree, but it's not known whether there's one. So the new result is about the Euler characteristic of this graph complex. So the Euler characteristic is just the alternating sum over the Betti numbers over the dimension of these homology spaces or groups. And yeah, the theorem is a formula for this Euler characteristic for large T. So here's this formula. This Euler characteristic, it behaves asymptotically different depending on the parity of the loop order. So there are different behaviors if G is even or if G is odd. So in the even case, it alternates. And there's some constant that I call AE for the asymptotic behavior, some other constant BE, and that gives some exponential growth rate. And then there is some super exponential growth rate. And for the odd case, the situation looks much more funky. There's a similar constant AO, BO, And then there's another constant BO prime that moderates a sort of square root exponential behavior for large G. And then there's a kind of a complicated function fg and another super exponential term. That goes like g to the power of g over 2. So what is fg? So f of g is the funky part. So that's a sine of pi times g over 4 square root minus pi g 4 plus 3 over 8 pi. So this means that for odd g, this Euler characteristic, it oscillates very widely, because this f of g function, it involves a sine of something which is a transcendental number. It involves the square root of pi times the square root of g. So this will at least almost never, actually it will be never close, it will be never equal to a multiple of pi. So the sign will never vanish, but it can become very close to a multiple of pi, this function, this argument. So the sign could become very small. And another, so a statement on the notation here. So a g tilde bg just means that the limit for g going to infinity of the ratio of ag bg, it's equal to 1. It's just a notation. And this ae, be, this stuff here, these constants, they are simple constants like, I don't know, 3 pi to the power of 3 over 2 over square root of 2, something like this. And I just didn't want to clutter the formula too much to actually write them down. And one thing that follows from this is that there's huge amounts of graph homology. So because of course the Euler characteristic is the alternating sum of the dimensions of the Betti numbers, and the alternating sum of course gives a lower bound on the total sum. So so it follows from this that the dimension of the total graph homology, so the sum of all the degrees at fixed genus, it's larger than some constant a to the power of g, or a times g to the power of g, or ag to the power of g over 2 for even g or odd g. And the explicit constants here are that ag must be just smaller than 2 pi times e. So it follows that there's like lots of graph homology. And this, it follows like non-trivially, slightly non-trivially. This is interesting. And this comes due to this oscillating sine function here. So because it can be, the sine can become very small depending on how close this argument comes to a multiple of pi. But this effect is countered by the large growth rate of this g to the power of g over 2 term. So actually, in the end, the sine function cannot really make this growth rate go away. And the tool that you have to use there is the irrationality measure of pi. So thanks to the fact that people have studied pi quite rigorously, and they know like what the irrationality measure is, we have a measure on how close to a multiple of pi we can get in this argument, and how large g has to be to get very close to this multiple of pi. And we can estimate this and see that it's like much less than this growth rate, and this growth rate can easily accommodate it. Some details for the proof. Okay. So something about the proof strategy, which is then again related to physics. Yes. You can look at this for only trees, yes. If you have, if you just, yes. This is actually very interesting. This is also, yeah, I didn't really think about this, but yeah, this is something that is also very curious about this. So I mentioned these two different sides, the even and the odd one. The odd one is actually more interesting in this case. So, I mean, we can just upgrade from GCG to GCGN, right? So we just add like leaves to the graph. And then we can say GC0N. And in the even case, this is something that is known as, it's called the Lie operad. And you can study its homology, but in the odd case, so if we do this odd, then the dimension of, I don't know what it is, top here. So the top dimension is precisely n minus 3 factorial. And this is very related to the n minus 3 factorial that everyone who does this BCJ and KLT recursions and so on very much likes.
I'm just curious how these things compare to the most naive. Everything is factorial to go.
I see. So what adding legs does to this number? This is also very interesting.
You're thinking about your G, but thinking about G loops as
yeah.
Being captured by cutting the loops down to get a tree. Get some super
I don't know.
You might pick it up for it. But already that's different, right? You have a G with a G in one case, a G with a G with two in another case.
Yeah, it's weird. Yeah. Right. No, yeah. But yeah, let me just say something about the proof strategy, or one possible proof strategy that I used. And this is, again, inspired from physics. So the combinatorial problem is very basic, because if you compute so this is strategy, or some bits and pieces of the strategy. So combinatorially, this Euler characteristic, it's the alternating sum of the Betti numbers. But it's like an ancient wisdom that one can just also compute this Euler characteristic using the dimension of the chain groups. And the dimension of these chain groups is just the number of graphs. So this is number of graphs of G loops with K edges and without automorphisms. So there's an entirely combinatorial problem that you have to solve to compute this Euler characteristic. And so this is about graphs, and quantum field theory is a fantastic tool to say something about the number of graphs. So there's a toy solution that does not quite work, but almost, from Q of t. So this is now from the Q of t manual. So you take some number, call it h bar. It's small, but slightly larger than 0. And you define a function of h bar that is given by the log of some integral. In this case, the integral is going to be from 0 to infinity. And we integrate something weird. We integrate over the exponent of 1 over h bar. And then there's some phi squared over 2 term, which is called the propagator suggestively. And then we have some interaction terms. And in this case, it's e to the power phi minus 1 minus phi squared over 2. And here's a minus sign, which is important. And we integrate this over d phi normalized with square root of 2 pi h bar. And so this looks like a very strange integral to consider, also with the log, but it's completely natural from like a quantum field theory perspective to look at something like this. And every quantum field theorist can tell you that it follows from this that this function I of h bar has an asymptotic expansion for very small h bar. So this is now asymptotic expansion notation. And in this asymptotic expansion of small h bar, we can write down some coefficients ag of and powers of h bar. So I shifted here by 1 for convenience. And it's very well known due to Wick and Feynman, and then also in this graph theoretical sense to the Itzigsten and Zuber, all physicists, that we can write these coefficients of these asymptotic expansions as sums over graphs. In this case, we precisely get sum over graphs G, and they have G loops. And for each graph, we take the minus sign to the power of the number of edges of the graph over the cardinality of the automorphism group of the graph. So each graph is weighted with the symmetry factor in physics, and this is a finite sum because there are not only finitely many graphs with G loops. And this strange combination of the exponential and the phi's here, there's a different way to write it. We can also write it as a sum from k larger than 3, phi to the power of k over k factorial. This ensures that all the minimal degree of the graphs is 3. And yeah, so the remaining task in the proof is just the tough task, is to remove this weighting here by these automorphisms. So we want to weight each graph actually with a 1 and not with 1 over odd g. So task, remove this So yeah, so this is just some sketch of the proof strategy, or one possible proof strategy. And if you ask, I can also tell you about like how to go further from this. But if I still have some time, or 1 minute, I can still show you some pictures. This is possible. Yeah. Okay. So I have some. So this is a picture of the homology of this graph homology. The y-axis is the degree, the k, and the x-axis is the genus or the loop number. And here's this kind of basic case of this graph complex. The gray wedge is just the support of the graph complex. So this is just the range in which there are graphs, and this dotted line is the line where these petals with the self loops are, so they're actually not really part of this thing anymore. Now we can add what's known on this graph complex. So this is the result of Wilbacher, that this blue wedge is vanishing for degrees smaller than 2g. And on this pink line here, there are these pink dots living, and they represent this this Grothendieck-Teichmüller-Lie algebra that kind of corresponds to the multiple zeta values. And these orange dots here, they are still explicit computations that have been done by a computer, and they go up to 10 loops. And this is also very interesting because these, also from a physics perspective, because these computations that are necessary to do this, they involve huge equation systems that have to be solved, and they are also huge sparse equation system. So the techniques necessary to do these computations, they are very similar to techniques that are used every day in high energy physics for the solution of these IVP relations. So yeah, and also people use finite fields to evaluate these homologies. So yeah, so this is how people computed these orange dots, and this is completely known up to genus 10, and up to from 11 on, we essentially only know this this pink line with the dots living on it. But we know that the number of classes here on this pink line grows exponentially. And now the new result is that in this red wedge, there's super exponential much homology hiding. So this is the summary from what I said before. Yeah. And now we can apply this using the result by Melody and Sam and Sören Gelasius to the moduli space of curves. And thanks to their result, this picture, it maps into this picture here that I have for the moduli space of curves. Here, this blue wedge is the stable cohomology of the moduli space of curves. This is very well understood. These are these kappa classes. They are also important in string theory, and then one can also use string theory technology to tell quite a lot about them on their intersections, for instance. And this cohomology has support here up to degree 4g minus 5. There's a sort of other Euler characteristic computation of this moduli space of curves, which is due to Hara and Zagier in the 80s. So Hara and Zagier, they showed the Euler characteristic of this moduli space that grows super exponentially. It actually grows like g to the power of 2g. So there's like lots of cohomology in this gray area, and we know also that it's not explained by the stable cohomology, because this is actually pretty small, the amount of stable cohomology that's down here. And then there are like some explicit computations, but these are very complicated. They use algebraic geometric techniques, and they go up to genus 4. And the genus 4 computation was done by Thomas in 2004, I think. And now we can map this picture from before into this picture, so we can combine both pictures, and we see that this pink wedge, it's flipped upside down, and it lands at the top of the picture. And this red line with the dotted beats, it's actually the topmost cohomology that is allowed to be non-zero. And there's exponentially much cohomology living here. And there are also these extra classes that are known. And so the image is sort of 3D, you have to imagine. And this is just the topmost slice of a cake, because it's just the top weight filtration in which this pink wedge lives. So there's like, possibly there's a lot of stuff under this pink wedge still living there. And the result applied to this or transferred to this picture is just that also in this top layer of this pink frosting on this picture, it actually contains lots of cohomology, and the amount of cohomology here also grows super exponentially. But here you can now compare the numbers. So this is the Harazagier result from the 80s. It grows like g to the power of 2g, the total Euler characteristic. And this Euler characteristic of this graph complex only grows like g to the power of g or g to the power of g over 2, respectively. So this says that in the other layers of the layered cake, there can be still more cohomology, or also in the gray area, and it's actually needed to explain this huge growth rate of the initial Euler characteristic.
Is that earlier computation also from an alternating sum that's then used as a bound, or do they know this one? Not cancellations in your.
This is because so this is a very good question. Yeah, so I skimmed over that. There could be computations, cancellations from everything, based on everything what I said. But if you think about it and look, and if you know that this weight filtration, it actually gives you a direct sum decomposition of the total cohomology. So if you know something about the top weight cohomology, for instance, its Euler characteristic, you also know everything about the non-top weight cohomology. And you just can compute it by subtracting like this large number from this one, and you still get something which is very large. So because Euler characteristic has this nice additive property over direct sums, you can actually, it follows really that there's like lots of non-top weight cohomology. Okay, it's a good place to stop. Thanks.
Any questions on mission? Yes, Alex.
So actually, I have two questions, and you can pick which one to answer. So first question is, so you showed low bound for this total dimension homology. Is there anything known about the upper bound? And the other question is there some intuitive way to see why even genus and odd genus have this different behavior?
So about the first question, so upper bound, yes, you just have to count like all the graphs. And yeah, I'm currently in contact also with experts on this. If one can use like very traditional like graph counting techniques on this, it looks as if, so yeah, for instance, there's Benny Sudakov or Nick Wormold is an expert on this. And I communicated with both, and it looks like that one cannot really take like a result from the literature and apply it verbatim to this. So one has to actually prove something. And yeah, we are thinking about it. But this is something interesting to do, like also get an upper bound. And it looks like that it also, it at least has the same like dominant growth rate. It's also like g to the power of g or g to the power of g over, no, it's like g to the power of g, I think, in both cases. But it shows that there's only an exponential divide, not a super exponential divide between the graph homology. So graph homology is still quite efficient, but it seems like it. And the second question, what was the second question again? Remember?
Kind of naive way to see why even and odd genus have.
Yeah, no. This is very weird that this is so different. Yeah, well, maybe one intuition is, so in the computation, the odd genus contribution that actually only comes from graphs with automorphisms. So a typical strategy in like these enumerative problems that tells you that you can ignore graphs with automorphisms because most graphs have no automorphism does not really work here. That makes the problem also quite hard because somehow all graphs with automorphisms, they cancel each other. Yeah, without automorphism, they cancel each other precisely, and you have to deal with all the automorphisms.
So if you count all the diagrams, you get G to the G. You should always get G to the G for the total number of diagrams. It's G factorial. But you're saying most of them are canceling, and so that's why you get something small. So this is
widely canceling in the Euler characteristic, and the sum over all the graphs should be much simpler. Computation actually.
That should be G to the G.
Yeah.
Can I ask, so in this dashed line, you have 3 dots at genus 3, 6, and 10. So only one at 15?
I don't know. Yeah, could be, but I think no one knows. Yeah, you can. Yeah, this is 15. I think if you have like a really, really expensive hydrogen-cooled computer, you might be able to figure this out in the next decade. But otherwise, yeah, you have to think about it. Yeah, yeah, yeah.
Is there a reason why most graphs you do are real graphs?
What graphs?
Like most graphs you give in as examples are real graphs.
Yes. Yeah, the reason is precisely because these are the only easy graphs that actually are non-trivial in this graph homology. So the wheel graphs, so this dot here is the wheel with 3 spokes. This dot is the wheel with 5 spokes. This dot corresponds to the wheel with 7 spokes, and so on. So, but there's like the brackets of the wheels still coming there, and so in a way, this all corresponds to wheels. This line here, and yeah, there's also these orange dots that are known to be non-trivial, but they are complicated linear combinations of graphs. So it's kind of hard to write it down. So wheels are simple examples that work. But there are also other representatives of classes, so they're just one choice. Okay. Yes?
Do you have any intuition on if you like expect some of the dimensions to be like close or very far away? How far away the actual sum is from the lower bound, or like? Or is it usually like really far away, or do you often have?
Yeah, so this is.
I don't know. Maybe this is kind of redundant given Alice's question, but I don't know.
Yeah, this is very interesting. This is just similar to the question what Alex asked. So what you can compute is also upper bounds, and yeah, so you can think about upper bounds also for this top weight cohomology and the total cohomology. And yeah, here you have to, for this modular space, you have to count ribbon graphs. Here for this red wedge, you only have to count normal graphs. And yeah, this way you could try to sort of constrain it from both sides. And this is like a very interesting thing to do. Yeah, good question. Yes? Yeah.
You should be able to do with a potential that instead of being your e to the phi minus 1, is log 1 minus phi. Because you want to have some of trace phi to the k.
Yes.
K.
Yes.
K factorial.
Right.
So yeah, presumably if you do a sample point analysis on that guy, you might get.
Yeah. Yeah, or do it with a matrix integral.
Sorry?
Or do it with a matrix integral.
That's what I meant. Yeah, you don't want to do it with a matrix integral, but instead of getting sum of phi to the k over k factorial, you want to get sum of phi to the k over k. Trace phi to the k over k. So
we would have to use the matrix model and then do the scaling limit just to get out only the planar ones. Yeah. But this is interesting, right? Yeah.
Any other questions for all right, if not, we can grab lunch and see you here at 2:30 for Thomas's line.